Hello, welcome to Chapter 2, Motion in One Dimension. This is going to be the start of our exploration of a concept called kinematics. So kinematics uh, is the study of motion without considering its cause. So when we get further into physics, we're going to talk more about what causes velocity and acceleration and displacement. But as it stands, we're just going to talk about the mathematical and graphical consequences of studying motion. So, position is the location of an object at any particular time. You can say that you're 5 feet away from the door, or 5 feet to the north of the door, or 5 kilometers north of campus. And all of that is giving a position. But what we need to talk about when we talk about position is reference frames, because different reference frames are going to give you different positions. So reference frames are things that are ways to look at a system and ways to think of it as stationary, even when one reference frame is moving relative to another reference frame. So, for example, as you go in your car, it seems like you're going to be stationary and everything is moving past you in the opposite direction. But if you were standing on the side of the road, you're going to see everything, the car moving past you while the trees and the road and everything stay still. So these are both different reference frames, and both of them are valid as long as they're not accelerating. And we'll get into what acceleration is in a little while. But according to Galileo, uh, and through most of classical physics, any reference frame that's an inertial reference frame, meaning a reference frame where the speed is constant, is going to have the same physics and is perfectly valid. So this is called Galilean reference frames, and it's pretty much uh, it's pretty much something that's going to be accepted and uh, useful up until you get to the 20th century, where relativity kind of throws a wrench in it. So, in addition to just talking about reference frame and knowing reference frames, we need to have a vocabulary for how to talk about these different ideals and these different quantities. So scalar is a number that gives you the magnitude of something, while a vector includes both the magnitude and direction. So a very specific or a very uh, easy scalars and vectors to understand are just distance and displacement. So distance is how much you've traveled. So that's a scalar, and it's what you read out on your car's odometer. So I have a job where I drive 40 to 50 miles every day uh, to get there, and then 40 or 50 miles back. So the 50 miles, so every day I have traveled 100 miles, and that's the distance traveled there and back. But displacement is how far you are from your initial position. So that is a vector, and it tells us just instead of just giving us a number, it says that I ended up, say, 2 feet to the left of my initial position, even though I traveled 100 miles in a day. So, uh, displacement would be something like uh, I From the Menifee campus, you are about, say, 100 miles southeast of Los Angeles. And then that gives you both the distance and the direction of what you're talking about. So these two units are measured in terms of feet, miles, kilometers, or meters, which is the SI unit. That's the standard unit for scientists that we use. But all of these are different ways to measure the same thing. So speed is another quantity that describes motion, and it is another quantity that you should be familiar with. So speed is the rate at which an object changes its location, and it's given by the variable v, where the average value of v is equal to distance over time traveled. So if you drive the 100 miles to Los Angeles over the course of 3 hours, then you would have 100 miles divided by 3 hours, which is going to be about 33.3 miles per hour, which is very slow, but maybe you're taking side streets the entire way there. And then the way that this scales is that a longer distance over a shorter time means that you're going faster. So if you manage to drive to Las Vegas, which is a couple 100 miles away, I believe, and you do that in 2 hours, then you're going significantly higher than 33.3 miles per hour. And then this is just the average speed, and speed is a scalar, which means that it just gives you how much distance you've traveled over time, and then the instantaneous speed is the speed at a specific instant, which is what is read on the speedometer of your car or in a radar or a police radar or something like that, where it's just talking about what you're traveling at that speed. So if you are going at if you're in rush hour traffic, or if you're going to Los Angeles and just get caught in the middle of traffic, it could take you 3 hours to get across the it could take you 3 hours to get from Menifee to Los Angeles, but a lot of that would be a lot faster, so 60 or 70 miles per hour going down the freeway, and then as you get stuck in traffic, it could be about 2 or 3 miles per hour. So the instantaneous speed is the speed that you're going at that instant. It's the 2 or 3 miles per hour, or the 60 or 70 miles per hour, while the average speed is the distance over the time traveled. And then velocity is going to be the vector version of speed. So velocity just tells you how far, what your displacement is over time. So it can have instantaneous or average velocity, but the way that it works is that you can go 60 miles per hour northwest. That's going to be a vector because it has both the direction you're traveling in and the magnitude. And that means that your speed is going to be 60 miles per hour, and your velocity is 60 miles per hour northwest. But if you ever change your direction, or go in the opposite direction, or change your direction at any point, then the displacement is not going. So say you go 60 miles per hour northwest for an hour, and then go due north after that at 20 miles per hour, then the average velocity is not going to be the same as the average speed, because you changed your direction and your displacement the absolute value of the distance that you traveled is going to be different. So it occurs to me that that was kind of confusing, so I'm going to come up with a simpler term or a simpler example. So if you go 60 miles per hour due east and then turn around and go 60 miles per hour due west for half as long as you were going due east, then your average speed is going to be 60 miles per hour because you were going 60 miles per hour the entire time, but your average velocity is not going to be 60 miles per hour because you went forward and then you went back. So your displacement from your original position is going to be uh, half as or a third as much as the distance that you've traveled. And then the SI unit for speed is then meters per second. And then acceleration is something that we're going to get more into next chapter. But acceleration is just a change in velocity over time in the same way that distance or velocity is a change in distance over time or displacement over time. Acceleration is the change in velocity over time. So when you speed up or slow down in your car, you are causing an acceleration, which is changing the speed that you're going. And the SI unit for acceleration is meters per second squared, which is meters per second, the SI unit for speed, divided by a second because it's the change in speed over time. So it comes out to be meters per second squared. So I'm going to try to avoid using too much algebra because that's not a prerequisite here. I do have to use variables because we need to describe how one thing depends on another, but I'm not going to rearrange equations that much or anything like that. I'm just going to leave it in terms of the variables that you're using. So what a graph does is show how one variable depends on another variable. So what we're going to see is how position depends on time or velocity depends on time when you have constant velocity or constant acceleration. So if the rate of change is constant, then the graph is going to be linear because the rate of change is equal to the slope at a given point. So the rate of change tells you how much something is changing over how much the y variable is changing over the x variable. So it gives you the slope at a given point, which if the rate of change is constant is going to just be a linear graph. And if the rate of change is constant, such as acceleration being constant, then the graph is going to be a parabola. So for constant velocity, we see that position versus time is a linear graph because you just as you go forward for this equation, for this graph, it's going forward at 1/2 kilometer per minute. So as you go forward 2 kilometers, or as you have passed 4 kilometers, then you've gone to, or sorry, excuse me there. As you have passed 4 minutes, then you've gone 2 kilometers. As you pass 6 minutes, you've gone 3 kilometers. And it just keeps stacking up so that distance versus time, or the position versus time is just going to be a straight line because you always have that same constant rate of change. And then if we look at the velocity versus time, this actually shows two velocities. But the first one that we're going to look at is from time in minutes from 0 to 10 minutes, which is going to be 1/2 kilometers per minute, which is the same as this graph right here. And then after that, it's going to be a constant negative 1/2 kilometer per minute, which would correspond to a different graph. But for that period from 0 to 10 minutes, you are going at a constant speed, you're going at a constant velocity. So therefore, you are just going to have a straight constant line always at 0.5 kilometers per minute. And then another thing to note is that because velocity is a vector, instead of just taking the absolute value like you would for speed, if you're going in the opposite direction, then you can have that negative 0.5 kilometers per minute like we see in this graph. So for constant acceleration, the displacement versus time, which is on the right this time, is going to look like a parabola. And the reason for that is because the velocity, instead of being constant like it was with constant velocity, is changing at a constant rate. So when you look at velocity versus time, velocity goes up at a constant rate with the slope being acceleration, because acceleration is the change in velocity over time. And then when you look at the displacement versus time, it's going to be a parabola, because instead of going at a constant speed, every little distance, time that goes by, you are going at a faster speed. You're going faster and faster and faster. So the slope of the line changes, which means that the velocity, or it means that the velocity is changing, so the slope of the line changes. So as the slope of the line is changing, that means that the velocity, or as the slope of the line is changing, that means that it goes faster and faster, which means that it's going to cover more distance over a shorter amount of time, which is why it curves up the way that you see here. So these triangles here show us delta distance over delta t, where delta means change in something. So this is the change in distance over the change, or the change in displacement over the change in time at point P and point Q, where P and Q are just labels for these specific times. And you see that the change in distance over change in time at point P is significantly smaller than the change in distance over change in time at point Q, because the slope at that line, or that those values give you the slope at or approximate the slope at that point, which is going to tell you the velocity at that point, because the velocity is change in distance over change in time, therefore, or the change in displacement over change in time, excuse me again. So the as you go from the, as you find the slope at those points, taking the change in distance from 30 seconds minus 20 seconds over 30 seconds minus 20 seconds is going to be higher than the change in distance as you take say it looks like about 15 seconds minus 5 seconds. So the change in displacement over 15 seconds minus 5 seconds divided by 15 seconds minus 5 seconds. So that gives the slope of the line, and that gives the velocity. So that hopefully wasn't too confusing. It's just how to read graphs, and even if you don't have an algebra background or anything like that, reading graphs is going to be a useful skill, and no matter what you do, you use it in offices, you use it as a scientist, you use it um, as an architect, you use it basically anywhere. So just understanding that the rate of change is equal to the slope is a valuable skill, I think, and will help you be able to better understand both this displacement versus time, this distance versus time, velocity versus time, all of these motion concepts, as well as allowing you to understand uh, just how things relate to each other and how things change when you're given graphs or charts in your everyday life. So thank you for your time. I am going to move on and see you in a second.